very nice you all came here tonight. I think the attraction is probably the cocktails. It's very nice that so many people here are so interested in cocktails that they're also willing to swallow some science along the way. That's why I also think it's a very good initiative. In fact, the last public lecture I gave was at the Kulturnat at the Niels Bohr Institute. And I really don't say it, I mean, with all respect for people over 60, but men over 60, but that audience was filled with entirely that population group. So it's very nice, different genders, different ages, and so I hope I can tell you something exciting about the quest for a fundamental theory of nature. Maybe I should say a little bit about myself. So I work as a theoretical physicist in the theoretical particle physics and cosmology, a lot of blah 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 names, group at the Niels Bohr Institute. That's a great institute, and it's of course, and I don't say this just to pleasure the Danes here, but it's of course a great privilege to work at such a renowned institute founded by the great Niels Bohr. In fact, well, you might think I'm Danish, but I'm not Danish, I'm Dutch. And you can permute the numbers a little bit, and I don't want to see anything into it, but believe me or not, I have had to explain sometimes, like, how can it be that you work in an institute named after yourself? But anyway, so I saw that the Danish translation for the title of this talk had the word jakt in it, and that's I was worried that's the right translation for quest. But in a sense, it's even more correct than quest. Jakt means hunt. And if you consider that truly in our field there are some very, very competitive but sportive people that all want to shoot, want to be the first ones that shoot the animal, then the word jakt is really quite appropriate. So what does it mean to find a fundamental theory of nature? Or maybe in other words, if this would work, yeah. Another way to start thinking what's a fundamental theory is to think what are fundamental questions you could ask, and the answers to those might lead you to the fundamental theory of nature. So here I've listed three fundamental questions. One is, what are the basic constituents of nature, or what we are built of, and what are the laws that govern their interactions? Like we also know it with people, you put them together, something happens, an interaction happens, and likewise it's with the smallest or particles in nature. You want to understand why they interact the way they do. Another sort of fundamental big question is how did our universe start, and what is its fate? I don't know, but I would guess that most people who breathe sometimes have this thought. Maybe not every night, but maybe you wonder sometimes what was before that and what's beyond our universe. Another one is that's a little bit more technical, and I will hope to partly explain the words in this question. So I don't expect you to understand this question, but what is the quantum structure of space-time? So actually part of the lecture will be what are the words behind it, and what is the proposal for an answer to this question. Now, in these questions, there are obviously two, in physics we have two tools to start addressing these questions. And one is experiments, so doing things, observing, and then seeing some patterns and making laws, and then applying it to other systems and seeing, hey, that works, or hey, that doesn't work. So that's the more step-by-step approach by observing. And the other is theory, and so that takes more a higher point of view, where you take some generally accepted principles or concepts, and you start to work from there, or with some hypothesis, and then you come to some conclusion, and then you maybe go and test it, and you see if it's right or not. If it's right, you're very happy, and you might even get a Nobel Prize. If you're wrong, you're, well, not unhappy, because you still had fun doing it, but you start trying again. And that's sort of life for most of us, just to be honest. And of course there's a big interplay between these two. Like theorists could be motivated by new experiments with strange results that they have to explain, and likewise experimentalists could be inspired by theorists because they have predicted some strange result. Well, those were very fundamental questions, but there are of course other important questions. And one is, can one mix science with cocktails? And like we all do, and that's not only physicists, everybody does this, our children, anybody we know, your mother. If you have a question, you just consult Google. So what happens if you Google the two words science and cocktails? And it's actually remarkable that it's all about the science of cocktails. There's nothing about, cocktails while doing science or science while drinking a cocktail. It's all the science of cocktails. So that's kind of telling. And here you see a picture. There's certainly cocktails involved, but you wonder how much science, even though they might give the impression. But if you still want to draw some parallels, then making a cocktail is a little bit like constructing a theory, and drinking the cocktail is sort of testing the theory. And like I said, I'm sort of the making a cocktail type. I mean, in work, outside work, I'm more like drinking the cocktail. But so this talk is also going to be mostly about the making the cocktail part. Although now and then I will mention, of course, some tests that are being done. But I'm sure, and maybe I've already had some speakers here that are more on the experimental side. There are some colleagues that can give you very exciting lectures about that. So let's see. There's like with a cocktail, there are some ingredients that you want to put together in physics. Now in the cocktail, it's very tangible ingredients like this a little bit of gin and a little bit of vodka and maybe a little berry. In physics, we actually have sort of two types of ingredients. One are rather tangible, and the other ones are the conceptual ingredients. So let me start with the conceptual ingredients that go into our way of thinking. And I will list three. This is one of them. I will spend really some time, I just gave some headlines, but explaining them. But it's really these three that I'm going to mention that is sort of the starting point of any physicist thinking about a fundamental question. So the first conceptual ingredient is space and time. If you just want to say it in ordinary day life, it's where and when. You all know you have sometimes an appointment here tonight, then that's 8 o'clock. That's when, and that's here at number 89, and that's where. That's of course our perception of space and time. For us it looks really like the time seems the same for everybody, and thanks to that our appointments actually fit, that you both show up at 8 o'clock. Space also, and that's really the, say it in an expensive way, the Newtonian way of thinking about space and time. Like time is the same for everybody, and space is something absolute. Like it starts here and you can just go on forever. But as you probably have heard, Einstein had some revolutionary thought, and I'll just give you the final result. It is a consequence of the fact that the speed of light is finite, but it's not so important. More the consequence of it is that space and time are not so absolute. Time is really dependent on what you do, in particular how fast you move. Like if you go faster, your clock actually goes slower. I mean, it's an actual. He predicted it, and it's an actual fact. And likewise, space. It also the way space looks really depends on what you are doing. So that was a big revolution. And last but not least, Einstein discovered that the very space-time, so space and time together, that we live in. So I hope, maybe I should emphasize again, to us they seem kind of separate, space and time, but you can really view them as one package. And in a sense you're also familiar with that because you live your life, but so meanwhile your time progresses and you move in space. So it's one big you could imagine looking at it sort of from the outside and seeing yourself moving through space and time. But so what Einstein found was also that the very space-time that we live in it actually starts to curve, starts to become sort of like a sphere, for example, instead of being flat, as a consequence of matter, so massive things being present. Okay, that sounds all very complicated, but just let me give you a useful thing to know. It's actually not funny, it's useful. So, when you go faster, clocks go, I always have to think, slower. On the other hand, so let's suppose you are on the Eiffel Tower, you're farther away from the center of the Earth, then you go faster, in fact. So, because of that effect, clocks go slower. But Einstein also found that when you go farther away from some massive object, and in that sense the Earth, then clocks go faster. That's another effect. One effect is actually goes under the name of special relativity, the first effect, and the second effect goes under the name of general relativity. Not so important, but the interesting thing is there are two effects, and this is why it becomes useful. It actually turns out that the effect of the clock going faster wins. So if you're on the Eiffel Tower, clocks go faster. So it also means that, you know, if you're like a big boss with a nice view, a high top skyscraper window, you will actually age faster. So keep that in mind if you get offered these high building offices. So, but that has also really been measured. So this is one very important ingredient that we use in physics. While the other is of course much more difficult to understand. That's the realm of quantum mechanics. And okay, in a nutshell, you might have heard of the so-called uncertainty principle. You can say it in one line. It says you cannot simultaneously determine the position of an object and the speed. I mean, the more you want to determine where the object is, the more accurate you want to determine that, the less accurate you know its speed, and vice versa. That's maybe hard to comprehend because, I mean, we all have a pretty good notion of where we are and what our speed is. But so and that's the fascinating thing, really, of quantum mechanics, that it's something very counterintuitive. But I think it also teaches us something. I mean, even as humans, in some sense, in the sense that, I mean, of course, our experience of the world around us is limited by the ability of our senses, right? How we can see and what we can feel and what we even can imagine in our brains. Okay, that differs for people, but still. So, quantum mechanics, I mean, just because something is very counterintuitive to your ordinary day life doesn't mean that it cannot be true. Right? It just means that it happens in a world that our senses cannot really see. Of course, we can then devise ways like experiments and accelerators, and I will get back to that to see it. But we ourselves can never become fully intuitively familiar with it. And it's actually, I mean, it is really also when I'm teaching students one of the most difficult topics. Also, was also for myself, in the sense that it's one of these things you just have to start accepting the principles and then work with. But you can never really fully comprehend. But the key words here with quantum mechanics, and that actually connects a little bit to cocktails, is fuzziness. That it's a world, the quantum mechanical world is a world where everything is a little fuzzy. And with fuzzy, I just meant what I said, that you cannot determine a position and speed with infinite accuracy. And as a consequence in quantum mechanics, you cannot say anything anymore for certain. All you can say is, you can talk about probabilities, so the probability that something will happen. It just happens for us that the probability that I'm standing here is extremely large at the moment, but I could be somewhere else. And you see that really more like, so these are, maybe I've heard of that in atoms, electrons go around the nucleus. I mean, that picture of sort of an atom circling around like the Earth around the Sun is a very inaccurate and simplistic picture. In a sense, what is described by quantum mechanics is sort of a blur here. These pictures showed it, indicating the likelihood to find an atom here or there. For example, there's a big likelihood to find it here and 0 here because it's black, and a big likelihood there. So quantum mechanics is about fuzziness. Then there's another, thermodynamics sounds also like an expensive word, but this is actually something we all can very much relate to, because it's all about energy and work and randomness and information. Sort of really what we feel in day-to-day life, that, for example, if your room is a big mess, you have to clean it up, it costs work. I mean, you know that, and there are actually physics laws behind it. And it's illustrated in this picture here with the black and the white sheep. That's a very disordered, messy configuration. And then the dog has actually to do work to separate the white from the black sheep. So these things are essential conceptual ingredients. Then also the more a la cocktail ingredients. The true tangible ingredients are in our way of thinking about nature is matter and forces. I actually hate showing this because it's so boring. Because I'm sure anybody who has come to any talk has seen these pictures, but still, it's sort of a mandatory thing to go through. And I will not spend too much time because most of these things could be known. But so, what we know about matter so far is that, well, we can go deep down in us, and then you find molecules, and the molecules consist of atoms, and the atoms again of electrons and nuclei, the centers. And then the nuclei consist again of so-called quarks. I mean, what's interesting here is that there's sort of a reductionism going on here, and the smallest particles we know now are quarks. And here they're drawn, they come in various colors, flavors, you name it. But the point is that we understand that quite well, these basic building blocks. And so the basic building blocks are basically quarks and electrons. Those are the smallest things we have seen. And then we know how these things interact with each other. And the crucial, there's sort of the list of 4 forces that act on these matter particles. One is gravity. Well, okay, that we're all very familiar with. And gravity is really a very special force in the sense that, to say it very scientific, it's universal. But universal, it means that it acts the same on everything. And that's really a very deep thing. It acts the same on you and me and on a feather and on a book. And last but not least, unless you believe in the Dan Brown books, but you shouldn't, there is no anti-gravity. So gravity is always attractive. And because gravity is always attractive, it accumulates. It can never cancel out, as much as certain authors may wish. And because of that, it feels very strong to us, because there's a lot of mass here on Earth. And all that gravity force has accumulated. But in fact, the other 3 forces, electromagnetism, the so-called weak force, and strong force, they're much stronger. They're the ones responsible really for, the electromagnetism for making the atom, weak for radioactive decay, and strong for keeping together nuclei. So it is, I mean, so gravity is very attractive, but that I actually stand here on the floor is thanks to these other forces that are so strong that the stone doesn't break through. Because it's really the force of the atoms holding together here that keeps me up. So in that sense, these forces win from gravity. So, but okay, I should maybe still say here that these 3 forces, and I shouldn't have gone so much back, gravity and the other 3. So gravity, as opposed to the other 3, they're sort of in conflict with each other. And what this hunt or quest for a fundamental theory has to do with is precisely resolving that conflict. So there's a conflict between how we understand gravity and how we understand these forces. And that conflict is, you can sort of, in a headline, summarize as Bohr versus Einstein in the following sense. So here you see them sitting. I mean, this is not, you know, your latest box world championship, Bohr versus Einstein. They disagreed on some things, but they sit there closely discussing, like we all do. But it's this clash between quantum mechanics, which I've tried to explain, you know, in a very simplistic way to you, and this uncertainty principle, this fuzziness, the clash between that and the theory of Einstein, namely general relativity, which describes everything that has to do with gravity, but not the other forces, that cannot really, well, that certainly in the 20th century couldn't be made to talk to each other. Now, it shouldn't be clear now yet to you what's the clash between these two, and I will get to it. But I first want to give some non-technical explanations, well, on the basis of quotes and a funny, well, not a funny, actually a nerdy joke. But sometimes these nerdy jokes and funny quotes, interesting quotes from famous people can say many words. So if you want to understand the uncertainty principle, there's a joke that goes like that: the policeman pulls Werner Heisenberg, one of the fathers of quantum mechanics, together with Niels Bohr, over on the autobahn for speeding. And the policeman says, "Sir, do you know how fast you were going?" And Heisenberg says, "No, but I know exactly where I am." And this is in essence like, you know, he invented this relation between not being able to know where you are and how fast you go at the same time. Then there's a famous quote by Niels Bohr, like, "If you aren't confused by quantum mechanics, you haven't really understood it." And that's it's from the father himself, and that's a very comforting thought, because it is really counterintuitive, as I said. Then Albert Einstein explaining relativity a little bit here. That's like when you're courting a nice girl, an hour actually seems like a second. But when you sit on a very red hot cinder, a cinder is a piece of burning wood, a second seems like an hour. That's relativity. So that summarizes, in some sense, Einstein's theory of special relativity, in the sense that what he really means to say here is that the notion of time depends on the observer, right, and on what the observer is doing. Now, to understand this clash between quantum mechanics and the theory of gravity, so Einstein's theory, I have to look a little bit at sizes in the universe. And here's the so-called cosmic Ouroboros. And I wish I could do Tom Hanks's voice now, and I would sound like Robert Langdon, because this is some ancient symbol of reflexivity and self coming together and the eternal. So it's a snake that bites itself in the tail. But it's a very nice way. Of course, the ancient people didn't have all these pictures on it; they just had the snake. But we as we as physicists, we can put the pictures on. And what's depicted here is length scales, so sizes in centimeters, going. I'll explain in a second what this is, but because you might not be all familiar with this notation, but going from the very big to smaller and smaller, and the very small. And so 10 to the 30 centimeters. I mean, it doesn't really say me that much either. I just know it's a 1 with 30 zeros. So it is very big, but what that size is, it does tell me something. That's the size that we at least think we know is the size of our universe now. So that's sort of the biggest size we know. Then if you go down, the numbers don't really matter, but it's more interesting to see what happens when you go down. Then you see galaxy clusters. Next scale down, galaxies, stellar constellations. Here, like our solar system, the sun, the earth, a big mountain, us, ants, the bacteria, DNA. So over here we're really going into smaller and smaller atoms, nuclei, so the things that sit here in the atom. And then actually, then there's a big question mark there. It stands there DM. It means dark matter. I'm not going to say so much about it. Maybe Holger Nielsen did in his talk. But that's sort of precisely the unknown regime that particle accelerators like the one at CERN in Geneva are trying to see what is out there. So it's a big question mark. But really, all the way here, there is a length scale, which I will explain a little bit more detail in the next transparency, which is what we believe the smallest length that makes sense to think about. And you might think, I mean, how can that be? Because I have something small, and I can always divide it by 2 and be even smaller. But from some basic principles and fundamentals of physics, there is the smallest length scale. But before talking about that, I just also want to point out, which I think is quite interesting, that we humans are sort of the very average. We're sort of in the middle of all this. And it's I think, well, I'm not so that everything has to be related to the reason of life. But you might wonder, maybe precisely that we are sort of in the middle of things makes it possible that we exist. I mean, certainly it would be very inconvenient if we would be as big as the universe. I mean, that's clear. It would also be quite inconvenient if we would be this small out there. So, but that we're sort of halfway down is quite fascinating, I think. But so, what is this smallest scale? Okay, this smallest length, so the smallest possible size for which it makes sense to consider space is the so-called Planck length. To put it a little bit in perspective, so this theory of quantum mechanics, this fuzzy theory that is so difficult to understand, has nevertheless been tested down to an incredible short distance. That's a trillionth of a centimeter with an extremely high accuracy. That's what particle accelerators do for you. So that it just works extremely well. What happens is that you can show, and I'll say in one sentence what kind of happens. That is that if you just want to marry gravity with quantum mechanics, then something really breaks down at even smaller distances, 10 to the minus 33 centimeters, called the Planck length. A way to visualize it, like somebody standing here, magnify him 10 billion times, then you would see actual atoms. But if you then, on top of that, start to magnify, put a magnifier of like a trillion times, then you get down to this length. So, I mean, it's no wonder we haven't seen it yet. But it is a fundamental problem with our way of thinking about quantum mechanics and space-time, being where gravity lives. And so what we need to resolve this is a new theory called quantum gravity. That's a logical name. It should be how gravity starts to be like when it's quantum. And it should incorporate the quantum nature of space-time. Now here's maybe a little bit more. So our usual notion of space-time, I mean even for us personally, but also in Einstein's theory, is space-time is something very smooth. It might curve a little bit and there might be some ripples on it and some waves. But what precisely happens at the smallest length scale, the Planck scale, is that the whole sort of turbulent, chaotic world of quantum mechanics starts to enter the game. And that's sort of depicted here. So space starts to branch off in strange ways, and it becomes just a very messy type of structure. And in particular, it's precisely at this length scale that if you would want to go down to this small scale, black holes would start to form, destroying the space before you could even look at it. I mean, that's one way to think about why can't I make it smaller and smaller and smaller, because at some point black holes will form. and I will, if I have time, get a little bit to black holes, but that's not good for your space-time if the black hole starts. I mean, it also sounds bad, right? A black hole. It doesn't sound like a positive thing that can happen. So what to do? Well, science plus booze equals string theory. Brings us back to this. I actually didn't make this drawing. You can find it on the web. And he says, I'm telling you, man, it's all made out of these tiny dancing strings. And that's sort of how our theories arise. Because even though I said I cannot find anything on Google about science and cocktails, whereas we often sit behind our desks doing tough calculations and ponder, actually a big part of our daily life is to talk to other people. And that could actually really, and it will, happen over a cocktail. So, string theory then is a theory that is a proposal for a theory of quantum gravity. A theory that solves these problems of marrying quantum mechanics with gravity. Beyond this marriage between these two seemingly inconsistent theories, it has also other big aims that I will just list here. Like, it would like to just be able to explain all known particles and beyond, and the ones we still have to find. It should be able to describe the physics of black holes, something that's, black holes have some very curious properties, and it's precisely also there that to explain these properties of black holes, you need to have a theory of quantum gravity. And then you can test if string theory can do that. Even more grandiose, it should be able to explain the Big Bang, how it happened, was there something before, and how will it end? Okay, that's the question of cosmology. It actually is a very simple principle that I will just show in one transparency, but the mathematics gets quite involved. But it's reasonably simple to explain in pictures. But it has this sort of aura over it that, oh, it's so mathematical. That's true, but there are also other fields that are so mathematical. So the idea in string theory is that, unlike what was thought before, that the fundamental building blocks are particles, so point particles that move through space, and that you and I consist out of point particles, that we replace that idea by saying, no, that's just an obfuscation. I mean, if you just think about a little string and you look farther and farther, at some point it starts to look like a point. So you can be easily, say, mistaken. So let's take as the fundamental building blocks strings, really like strings, like violin strings, in the sense that they can also vibrate, just like violin strings. And here I've drawn a string and some vibrations. And of course there's a lot of mathematics behind it, but you can really see these different vibrations of a string, like the tones of a violin. But in the particle theory language, these different vibrations of strings are then different particles. So that's already a very beautiful feature, that you have one object, one string, that describes at one time many different particles, just by having the different tones, so to speak. Not only that, it turns out that one of these particles is a very special particle, namely the so-called graviton. It sounds very fancy, but you have now heard the word gravity. That has to do with, falling down. And the graviton is supposedly a particle that mediates that force. So that makes the things attract, that makes us attract, for example, to the Earth. So one of these particles is this graviton. And that's very remarkable. And okay, this is as technical as it will get, so don't worry, it will become fun again. But I have, in the sense that if you now start to collide strings with each other, then strings have a very nice property. Like, so here you have a string, this round thing. It starts to move. This one starts to move. It hits each other, and it comes out again there. When they collide with each other, these things are much better behaved, as I hope the picture can show, than when point particles collide each other. This is a very singular, we call point. I mean, it just happens at one point in time and space, and it's this that makes it impossible to incorporate this fuzziness of quantum mechanics. And so the intrinsic size of the string here gives automatically sort of a fuzziness, and you cannot really say when they meet here. It could be here or here or here. And in that sense, string theory solves this problem that ordinary quantum mechanics has with gravity. Does string theory actually make some predictions? It makes some general predictions, like supersymmetry. That sounds very technical. I will not talk about it. But one other prediction is, and that's more, playing to the mind, I think, is extra dimensions. So, what do we mean with extra dimensions? So, string theory actually predicts 6 extra space dimensions, except the 3 that we know, going here, there, and up. Forget the number 6. I mean, it's already nice if you can visualize 1 extra dimension. Don't get frustrated if you cannot visualize 6. For me, that's also hard. But one can try. I made here but the way you should think about it is that really at each point in our space, there are attached, extra, rolled up, small, but very small dimensions. They're just so, why don't we see them? They're really so small that we cannot walk into there. And it's really not, I just want to say, if they are small enough, it's not surprising we haven't seen them. Just to visualize it even better, I mean, suppose you had a 2-dimension, a sheet here, just a piece of paper. Obviously, that you call that there are 2 dimensions here. You can move this way or you can move that way. If you now roll it up like so, and you roll it very, very, very tightly, well, you can, as easily as before, just move this direction. But if you're too big, it will be extremely hard or impossible to go around here. I mean, you have to be an ant, or, the smaller you roll it up, the smaller you have to be to go around. So the whole idea of these extra dimensions is they're so small, they're like small rolled up, curled up dimensions that only the tiniest of particles can actually go around them. And will this actually be tested? Well, if they exist, and that's a little technical proviso, if they are small but still large enough, so not too small, then we might be able to see them in this Large Hadron Collider in CERN. You probably have heard about it because it got a lot of publicity lately, also some negative publicity, but it's working now. There's a big accelerator here close to Geneva where they shoot protons, certain particles, and antiprotons on top of each other, and then they examine what comes out of these head-on collisions. And one of the things, among other things, that they want to test there is, do there exist extra dimensions? Looks a little bit like a fancy diagram, but what I mean to say here is that one way you can infer the existence of these extra dimensions is if you see some missing energy. Normally, energy should be conserved. And suddenly you see energy disappearing. And that is because some particle, like for example a graviton that we talked about before, has disappeared in the extra dimension. And one would be able to see that if it happens. So that's exciting. I will skip some of this because I think... so there are also astronomical observations that you could do to verify some aspects of string theory, but those are a little bit more far-fetched. Do I have 5? Where is the chairman? Okay. I'll round it off in 4 minutes. So I just want to say a couple of words about black holes, because, like I said, black holes are very beautiful and important testing grounds for these new ideas about space and time and quantum mechanics. And actually, so one of the reasons is that black holes are hot. And with hot, we just mean here that they radiate energy. And so there's a famous paradox that if you throw in a chair into a black hole, then it gets absorbed by the black hole and just gets emitted in radiation, in heat. But in a very special way. Namely, once the chair has fallen into the black hole, there's no memory anymore of the fact that there was a chair that fell in. It could also be anything else. And, well, you might say, well, fine, if I light the chair, then the chair is also gone, right? If you burn the chair. But actually, strictly speaking, according to the laws of physics that we know, if you burn a chair, put it on fire, and you had the power to analyze all the smoke and dust and ash, you could reconstruct the chair out of it. That's what we learn in ordinary physics. But in a black hole, you could not. And once it has fallen into the black hole, the information about the chair has disappeared. And that's against our rules, so to speak. So these paradoxes have to be solved in some way, and string theory does that. I will, because I really don't want to keep you longer than this, so I'll skip some black hole slides and sort of move to the end. I can wonder a little bit really what is a black hole. It has some nice properties, but I will skip over them. One thing that I will just say is that here's a nice picture to visualize a black hole. And if you really cannot imagine black hole, imagine this. Imagine you're sitting in a rowing boat close to the Niagara waterfalls. I mean, that's how it is to fall into a black hole. You row, I mean, you go with the stream. I mean, this is a picture of a black hole. You go with the stream, and at some point, you just go down the Niagara waterfalls, and you never come back. That's sort of why they're called black. There's only a way of going in, and in particular, even light cannot escape. That's why they're black. But I think these pictures are, even though they're oversimplified, they tell you quite a lot. It's like you can only go in, not out. And black holes are really no science fiction. I should really stress that in the sense that we see black holes around in our universe. For some time people thought it was science fiction, but we know they exist. So here are some pictures of black holes that we know exist in our universe. Now string theory has actually, that's the last thing I say about string theory, a very new way, and that's also why people are in part excited about it, of seeing black holes. And that's because string theory is not only a theory of strings, it's actually also a theory of brains. It sounds very fancy, but just like a string is like a one-dimensional thing, so a little violin string, a brain is like a membrane, like the top of a drum. That's like a brain, a membrane. And what you can now sort of think about is that strings can sort of end on these brains. And it's this type of thinking of the interaction, the way strings are being kicked off drums, brains, that one can understand black holes. So this not understood radiation of a black hole can really be seen as strings being thrown off these brains. Now there's been a lot of talk about, oh it's very scary, CERN mini black holes will form and will eat the Earth. And this is for me really an example that there are people in our world with too much time, because here's actually a picture of what they say could have or would have happened on the 10th of September 2008 already when they turned it on. So, but I found it very funny. Here a black hole starts to form and starts eating CERN, and in fact there's a whole cascade of transparencies that show that first Geneva and then the whole Earth would be eaten. But it's always nice for experimenters to be able to say, we're pleased to announce we're still here to report the results. And we hope it will stay like that in the future. So string theory, it also addresses the bigger cosmological questions. I just want to point out this one picture here that there are people that think that maybe we don't live in a universe but in a multiverse. these should be then different universes. So at each point of time, new universes start to emerge and start to end again, and we're just part of a whole bigger super consciousness of multiverses. That is pretty hard to test, I think, because I mean it is. But there are some people who think one can make actually predictions based on that. The future will tell. So to conclude, 21st century physics is quite exciting in our field, in the sense that we have to confront string theory with particle physics and cosmology. As I try to argue, the whole way of thinking about space and time has to be changed a lot. Very new fundamental principles should come in place. I think one should also, when you give a talk to the general public, say, why should we care? And then there's a beautiful quote of Einstein. If we knew what we were doing, it would not be called research, would it? That's one way to answer that question. Niels Bohr said, I mean, you can ask, is it useful for something we're doing? Prediction is difficult, especially the future. It's also very true. But okay, there is a more like serious list you can make about why you could care. First, intellectual curiosity. Well, that goes a little bit more along the lines of what Einstein said. This actually goes a little bit along the lines of what Bohr said, in the sense that you can never really predict the impact of scientific discoveries. Quantum mechanics is a very good example of that. Without that, we wouldn't have our iPhones. There are, of course, spin-offs, many spin-offs to other areas. I could give a whole lecture about that. There are many other innovations, like World Wide Web, came out of particle physics. General relativity, as strange as it might sound, these things that I say that all clocks start to move different when you go in a different speed. Without GR, we wouldn't have our GPS, our global position system. You wouldn't really, I mean, if you wouldn't correct for these theoretical predictions that Einstein made in 1916, 1930, after 1 hour driving, your car would be, I don't know, 100 kilometers off. So these things are turn out sometimes to be very important for applications. Okay, then I want to, this is the last transparency, conclude with some so-called Rumsfeldian epistemology. I hope you have heard of Donald Rumsfeld, excellent Secretary of Defense. He was not only an excellent Secretary of Defense, he was also a great philosopher. And he popularized in some briefing at the Department of Defense, talking about the Iraq War. He popularized the following poem. Like, there are known knowns. No, those are the things we know that we know. There are also the known unknowns. Those are the things that we know that we don't know. But then also the unknown unknowns, right? The things we don't know, that we don't know them. And I really say that not to honor Rumsfeld, but, and of course, unknown unknowns have been long known in epistemology. He just popularized it. But it is precisely this kind of frontier that is, in a sense, the most exciting for us. The things, not in part the things I talked about, but what's even more exciting for us is what's beyond there, but we don't know yet. And okay, I will conclude here. Thanks.